Good afternoon. Let us start our lecture today. So last time we were trying to solve the elliptic equation. So the elliptic equation that we were trying to solve last time was this one, minus 2 second u plus u is equal to f. So this is on 0, 1, and u0 is equal to u1, and they're both 0, right? So u is a function of x, and f is a function of x, right? And our method is the following. Our method is to use the which form, right? So v will be a test function, and then you multiply v to this equation, you integrate, and you get right. So this is going to be our weak form. The weak form is the fact that you can multiply both sides of the equation by a test function and you integrate both sides, right? So when you do the integration by part, what you get is the interval from 0 to 1 of u prime v prime plus interval from 0 to 1 uv, and this is equal to the interval from 0 to 1 of f. All right. Now we're gonna have from this form, this will be buv, and this will be lv, right? In the Laxman theorem. So v will be a bilinear form, symmetric in u and v, because if you fix u, so in here, if you fix u, it becomes a linear mapping in v, and if you fix v, it becomes a linear mapping in u. All right. So here, this is the form when you use the Laxman theorem. So in Laxman theorem, what you need is the Hilbert space H. Right. So the Hilbert space H, in this case, will be, you're gonna take into account this boundary condition and the condition that B is verified. Right. So in the last class, we define v u to be u, which is a function in from u to 0 to 1, such that u at 0 is equal to u at 1, and this is 0. So this is the condition of the Hilbert space. And we also require that this norm 0, 1 is finite. So right, so we require that, okay, the condition at 0, boundary condition at 0 of this function and the condition at 1 of this function, they're both 0, and this function belongs to W1 to 0, 1. And so we call this space W0, 1, 2. So the 0 here means that you have 0 boundary condition. All right. So we said in the previous class that the norm of the, so if you in W1, 2, right, you can also express the norm of this guy to be the L2 norm of u prime square dx 1/2. All right. So in the previous class, we also discussed that, okay, if you consider this W1, 2, so if you consider this W1, 2, so instead of considering the full norm W1, 2, what you have to do is just to consider the L2 norm of the derivative, right? So there's no one, right? Right. So and now what we have to prove now is the equivalence between the two norms in this space. All right. So to show that, I'm gonna show that the L2 norm of u prime is going to be bigger than the L2 norm of u, right? And this is the so-called Sobolev embedding. So so this is one of the overlap embedding inequality, and we're gonna prove this one. So in the previous class, what we proved is the following. So the goal is to show that the L2 norm of U prime is going to be bigger than L2 norm of U, right? So this is our goal. Our goal is to show that L2 norm of U prime is bigger than the L2 norm of U. How do we show that? So in the previous class, we're gonna we wrote ux minus u0 to be the integral from 0 to x of u prime of t dt, right? So this is only the definition of derivative, right? So antiderivative, right? So you take the antiderivative of u prime, you get ux. So now, because in H, you know that u0 is 0. So in this case, ux will be the integral from 0 to x of u prime t dt, right? So then I can take the absolute value. This is smaller than u prime of t dt, right? Now, I want to have an L2 norm here, right? Because here I have the L2 norm of u prime. And so here I have the L2 norm of u prime. Here I have only the L1 norm of u prime. What should I do? So in order to estimate the L1, yes?
Use Holder's inequality.
Yes, so Stephen's idea is correct. So this is basically what you have to do is to use Holder inequality. So here you use Holder inequality, and what you get is that, okay, this is going to be smaller than the integral from 0 to 1 of u prime t. So that u prime t square dt 1/2, and then I'm gonna have the integral from 0 to x of 1 dt of 1/2, right? So this is, yes. So so here I'm gonna use a Holder inequality. So the L1 norm of u prime can be bounded by the L2 norm of u prime and the L2 norm of 1, right? So because 1 from u prime will be u prime, right? So now you're gonna have the integral from 0 to x of u prime t dt. This is going to be smaller than the L2. So because I'm integrating from 0 to x, but x is from 0 to 1, so this is definitely smaller than the integral from 0 to 1, right? So this is going to be smaller than this guy. So remember that here I replace x by 1 because x is smaller than 1 and x is from 0 to 1. So this guy becomes antiderivative 1 is x, right? So this will give you x 1/2, right? So then here,
I think
what I
so.
get, yes. Yes.
I was going to say that even if you weren't in 0 to 1, if you wanted to extend this, you just have the size of x on one side or the norm of x on the right-hand side. So then you can just normalize the left-hand side, right?
So you want to put 1 here, right? Or what? I don't understand.
So on the right-hand side, right?
This one.
So you have the integral 1 from 0 to x. Yeah,
Yes.
so that's the magnitude, right? So then
So
if you wanted to extend this on a longer interval.
Right, because we are solving the problem from 0 to 1.
I'm just okay. I'm just saying that if you wanted to extend the interval, then you could still do it with this, right? You could just normalize.
Yes.
Okay.
But this x is smaller than 1, so it's fine that you extend it because so this is smaller than this, right? So this is smaller than this, so it's fine. So the integral from 0 to x is smaller than the integral from 0 to 1, right? And because x is from 0 to 1, so I can bound this one by this quantity. and this is still fine, right? So so what I do is the following. So this is so this is u prime t square dt 1/2. So this is x 1/2, right? And this is smaller than interval from 0 to 1 of u prime t square dt 1/2 x 1/2, right? It's good. So this guy is smaller than this guy, but this guy is bigger than this guy, so it's fine, right? So this is smaller than this. This is smaller than this. This is smaller than this. So this is smaller than this, right? All right. So now what I have is that, okay, u prime t dt. So this x is again smaller than 1, so I can bound this by 1. So this is going to be smaller than 1 ut prime 1/2. Since x is smaller than 1, right? Because x is smaller than 1, I can bound x 1/2 by 1, right? So which means that I have the interval from 0 to x u prime t dt is going to be smaller than interval from 0 to 1 of u prime t squared dt 1/2, which is the quantity that I want. All right, now, but this guy is again bigger than ux, so which means that ux, so this guy is bigger than ux. So ux is again smaller than this quantity, which is the L2 norm of u prime, right? So to show that the L2 norm of this, so from this, how can I deduce the inequality that I want? I explain again. I write out the definition of u prime, right? So ux minus 0 will be the interval from 0 to x of u prime t dt. So u0 is 0, so ux will be the interval from 0 to x u prime t dt. Now I take the absolute value. So the absolute value of ux is going to be smaller than interval from 0 to x u prime t dt, right? I apply Holder inequality. So the interval from 0 to x of u prime t dt is going to be smaller than the interval from 0 to x of u prime t square dt 1/2. And then here I have the interval from 0 to 1 of 1 dt 1/2. So I bound this quantity by the interval from 0 to 1 of u prime t square dt 1/2 x 1/2. So this guy is smaller than this guy, but this guy is smaller than this guy, meaning that this guy is also smaller than this guy, right? All right. So so again, I bound x by 1. So which means that from here, I have the interval from 0 to x of u prime t dt is going to be smaller than the interval from 0 to 1 of u prime t square dt 1/2. So this is the L2 norm of u prime. Now I have ux is smaller than the L2 norm of u prime for all of the x in 0, 1. This is true for all of the x in 0, 1. How do I get from here to the inequality that I want? Right? So ux is bounded pointswisely by an L2 norm of u prime. My claim is that the L2 norm of u is also smaller than u prime, the norm L2 norm of u prime. Why? To see this, okay, so let me write out the L2 norm definition of L2 norm of u. So definition of L2 norm of u will be ux square dx interval from 0 to 1 1/2, right? So how can I show that L2 norm of u is smaller than the L2 norm of u prime? Right? So I have just proved that ux is smaller than u prime L2. This is true for all x that I want. Now the L2 norm of u will be integral from 0 to 1 of ux squared dx 1/2, right? So how can I go from here to here? You just have to plug this inequality inside and you see. So ux is smaller than u prime norm. So here I put u prime norm square, and this is square dx, and this is 1/2, right? But this norm is a constant, right? So which means that this is the, so when you integrate this guy, you got u prime square L2, and then you have 1/2. So this gives you u prime L2, and that's it. So basically what you have is u L2 is smaller than u prime L2. I explain again. After all of the complicated things that I just showed you, I have that ux is smaller than the L2 norm of u prime, right? Now, because ux is smaller than the L2 norm of u prime, I consider the L2 norm of u. So the L2 norm of u will be the integral from 0 to 1 of ux squared dx 1/2. And then now I have the integral from 0 to 1 of u prime squared dx 1/2. And so because I bound ux by this L2 norm, but this L2 norm is a constant. So when you integrate in x, it's going to give you again this constant. So then you're going to have u prime the L2 norm square, and then you take the power 1/2. So this is basically the L2 norm u prime, right? So which means that the L2 norm of u is going to be smaller than the L2 norm of u prime. It's clear? Questions? Good. So now what I have is the following. I have in the space of H, which is W 0, 1, 2. So in this space, I have two norms. The first norm is going to be u square plus integral of 0 to 1 of u prime square 1/2. And the other one is only the u prime square, right? And I say that the two norms are equivalent. The two norms are equivalent. All right. So on this W12 space, I have that I have two norms. The first norm is the standard W12 norm. The second norm is the standard W120 norm, which is only the L2 norm of u prime. And I am saying that they are equivalent in the sense that they are constant C1, C2, such that for all of the u in W12, you're going to have C1 u W12 to be smaller than u W12, but this is smaller than C2 u W12, right? So I'm saying that those two norms are equivalent because of the fact that, okay, if there exists two constants C1, C2, such that C1 times the W012 norm is smaller than the W12 norm, but the W12 norm is also smaller than another constant C2, the W12 norm, W120 norm. So who know why?
Does this have to do with the Fourier transform formulation of Sobolev space?
No, it is the effect of the Sobolev embedding theorem that I just showed you. Can you see why? So what is the Sobolev embedding? The Sobolev embedding say that, okay, the L2 norm of u prime is going to be bigger than the L2 norm of u. Or equivalently, you don't have to take those 1/2 outside. This is the Sobolev embedding theorem that we show. We show that, okay, the L2 norm of u prime is bigger than the L2 norm of u, or the integral from 0 to 1 of u prime square is bigger than the integral from 0 to 1 of u square. right? So let us prove it. So the C1 here is easy. So what is the value of C1? Right? So I want to show that there is a constant C1 such that the C1 times the W012 norm is going to be smaller than the norm of U in W12. Right? So what is the value of C1? So this is how, so this is straightforward from this form, right? So this form you have two quantity, and this form you have only one quantity. So which one is bigger?
Is it 1/2?
So this the first one is bigger, right? So the first one you have the U square and the U prime square, and the second one you only have the U prime square, meaning that okay, this one has to be bigger than this one. So C1 is just 1, right? So you have what? You have clearly that this is smaller than U square, because here you have two quantities, right? Here you have only one quantity. So then of course this is smaller, right? So now if I take the 1/2, all right, and this is still the same because they are positive quantity, right? So which means that you have the W012 norm is smaller than the W12 norm. All right, good. So what is the value of C1?
1.
1, right? So of course C1 has to be 1. I explain again. So I pick any function U. I define the W12 norm to be the integral from 0 to 1 of U square plus the integral from 0 to 1 of U prime square, 1/2, and the W012. So the 0 means that the boundaries are 0. So this not so in this norm I'm gonna get I'm gonna throw away this quantity, right? I want to keep only U prime. So of course, because here you have one quantity and here you have two quantities, of course the one of so this one has to be smaller than this one, meaning that the W012 norm has to be smaller than the W12 norm, and which means that C1 is definitely 1. Now the second terms is much harder. So it's not much harder. It's not straightforward like this. So you want to show that there is a constant C2. So this is true for all of the U in W12, 0. And this is true for all of the U in W012. All right? Now, so I want to find this C2. All right? So what is the meaning of this C2? This C2 means that, okay, so you're going to have the integral from 0 to 1 of U square plus the integral from U1, U prime. So if I square both sides, here I have C2 square, right? So now I have this is smaller than C2 square, the integral from 0 to 1 of U prime square. Right? So the second direction is I have to show that there is a constant C2 such that the W12 norm is smaller than the W012 norm. All right? So the W12 norm is the integral from 0 to, so I'm taking the square, so because here I have the 1/2. So the W12 norm will be the integral from 0 to 1 U square plus the integral from 0 to 1 of U prime square, and here you have C square, and here I have the integral from U prime square, right? And I'm telling you,
is it
yes?
√2?
√2, yes, sure, absolutely. So Stephen said that C2 is √2, which is correct. Why? Because you from this inequality, you know that this is smaller than integral from 0 to 1 right, of u prime square. And here you have another term, which is integral from 0 to 1 of u prime square, right? So which give you integral from 2 times integral from 0 to 1 of u prime square, right? Because this is going from the superlap embedding theorem. The superlap embedding theorem said that the L2 norm of u is smaller than the L2 norm of u prime. So here you have the L2 norm of u square, and here you have the L2 norm of u prime square. So this guy is definitely smaller than the integral from 0 to 1 of u prime square, and you keep the same thing here. Finally, you get 2 times integral from 0 to 1 of u prime square, meaning that C2 is square is 2, and C2 going to be square root of 2. So according to Stephen, right? It's clear. So basically, the two norms are equivalent. So which means that I'm gonna have to use the W012 norm. I can use this norm, which is simpler, right? So now everything is fine because we have the H space number 4. So I'm gonna have to show this equation, which is BU V will be the integral from 0 to 1 of u prime v prime, integral from 0 to 1 of uv, and L2 not the linear form will be integral from 0 to 1 of fv, right? And the space will be the W120. In this case, it is also called W012, S012, right? So because we are in a bounded domain and in one dimension, so I can call this to be W012, and this is also S012. So this is the different name of this. So this is the Hilbert space. All right. Now I suppose that F is in L2. Yes. So before going to study F, we're gonna see that UV is bilinear, right? This is bilinear because if you have B of U, alpha 1 V1 plus alpha 2 V2, it's gonna give you integral from 0 to 1 of U prime of alpha 1 V1 plus alpha 2 V2 prime plus integral from 0 to 1 of U alpha 1 V1 plus alpha 2 V2, right? So first I see that, okay, this is a bilinear form. So this is a bilinear form because you can see that if I have B alpha 1 B1 plus alpha 2 B2, I can write as the integral from 0 to 1 of U prime alpha 1 B1 plus alpha 2 B2 prime, and then this is the integral from 0 to 1 of U alpha 1 B1 plus alpha 2 B2, right? And this is going to give you, because of the linear, so this is going to give you alpha 1 U prime V1 prime plus integral from 0 to 1 of U V1 plus alpha 2, the integral from 0 to 1 of U prime V2 prime plus the integral from 0 to 1 of U V2, which is alpha 1 B U V1 plus alpha 2 B U V2, right? So because you can write B alpha 1 V1 plus alpha 2 V2 as the form alpha 1 B V1 and alpha 2 B V2, right? So which means that this is linear in V, and similarly, you can also write B alpha 1 V1, alpha 1 U1 plus alpha 2 U2 V is going to be alpha 1 B U1 V plus alpha 2 B U2 V, right? So basically the linearity, the bilinear form is easy to see, right? So I explain again. This B is bilinear, which is quite standard because you can write B U alpha 1 B1 plus alpha 2 B2 as alpha 1 B V1 plus alpha 2 B U V2, and then you can write B alpha 1 U1 plus alpha 2 V2 U2 V as alpha 1 B U1 V plus alpha 2 B U2 V, right? So this is bilinear and coexist, meaning that BU U is bigger than alpha U square, which is W012. Why? Right, so I consider this bilinear form. This is definitely bilinear because this is standard.
From the inequalities that we just gave, from the equivalence of the norms.
Yes. So yes, but this is simpler than that because yes, you are right. So Stephen, idea is the following. Okay, so you have BUU will be the integral from 0 to 1 of U prime square, right? Plus the integral from 0 to 1 of U square, right? And this is definitely bigger than integral from 0 to 1 of U prime square, right? So in this case, alpha is 1. All right, I explain again. So from this, from the definition of B, Stephen said that, okay, this is coexist because when you write BUU, you get the integral from 0 to 1 of U prime square plus the integral from 0 to 1 of U square. And this is bigger than the integral from 0 to 1 of U prime square. So in this case, alpha is 1, right? So the next thing is that the boundedness. So the boundedness is the following. So you have BUV is going to be smaller than beta UV. So this is W012 and this is W012, right? So you have BUV will be the integral from 0 to 1 of U prime V prime plus the integral from 0 to 1 of UV. So how can I show that this operator is bounded? In the sense that I show that there is a beta such that BUE is smaller than beta, the norm of U times the norm of V. How can I show that? There is one way to do that. What is it? Yes?
You said.
Yes, Stephen? Right?
We just use a specific choice of V or U.
No, this is true for all of the U and
so
V.
that we can get.
So the boundedness is true for all of the U.
So we.
Right. So I have
pick
this
one.
Yes, I pick the first one, and I bound this one first. So how do I bound this term? How do I bound this term? There's only one term in all of this situation. What is it? Right, I have the interval from 0 to 1 of U prime times V prime, and then there is only one term to bound this interval that we use many times. And what is this term?
Holder?
Holder, yes, Molly is. Got it perfectly. So you have V prime L2. So this is Molly. Right? So Molly got it correctly, right? So you have what? You have the integral from 0 to 1 of U prime V prime is smaller than L2 norm of U prime times the L2 norm of V prime. So this is nothing but the W012 norm, right? Because the W012 norm is the L2 norm of U prime. Now I pick the second one. How can I bound the second one?
The same way.
The same way, right? So I'm gonna use Holder inequality. So this is different, right? So now I bound it the same way using Holder inequality. So the integral from 0 to 1 of UV is going to be smaller than the L2 norm of U times the L2 norm of V. But I want the W012 norm. How can I get it? right? So now I have L2 norm of U, and I want to bound that by the W012 norm. How do I do it?
Just using the inequalities we found earlier or proved
Right.
earlier.
So yes. So Molly is correct. We use the overlap embedding theorem, right? So using the overlap embedding theorem, we have that the L2 norm of U is smaller than the L2 norm of U prime. But L2 norm of U prime is nothing but the W012 norm, right? So this is like this, right? So now I can bound the first term by the product of the two norm, and the second term is also bounded by the product of so according to Molly, the second term can also be bounded by the product of the two norms. So what is the value of beta in this case?
2.
2, right? So in this case, Stephen said that beta is 2, which is correct, right? Because so when you take the absolute value of this bilinear form, this is going to be smaller than the integral from 0 to 1 of U prime V prime plus the integral from U to V. And then this is smaller than 2 times the norm of U and the norm of V, right? So basically in this case, all of the condition of Laxman theorem are satisfied for B, right? So in this case, we see that all of the conditions for Laxman theorems are satisfied for this B, all right? Now I'm gonna go to L. So this L V will be the integral from 0 to 1 of f V, and suppose that f is in L2, right? So f is the initial the given function, and I suppose that f is in L2. So definitely f is linear, right? L is linear, which means because L of alpha 1 V1 plus alpha 2 V2 is the integral from 0 to 1 of f of alpha 1 V1 plus alpha 2 V2. And this is alpha 1 integral from 0 to 1 of f V1 plus alpha 2 of the integral from 0 to 1 of alpha 2 V2, right? So this is f, right? And this is L alpha 1 L V1 plus alpha 2 L V2, all right? So L is linear, which is standard because you can write L of alpha 1 V1 plus alpha 2 V2 as alpha 1 L V1 plus alpha 2 L V2. Now, I want to show that L is bounded, right? So which means that I want to show that this is smaller than C times V in W01. So how do I show this? Right? So this is equivalent to the fact that I have the integral from 0 to 1 of fv dx is smaller than a constant C V times for all of the V in W012. So what is the value of this C? How can I bound this guy? I explain again. Now I look into the second quantity, which is the integral from 0 to 1 of f v dx. F is given, and I suppose that f is in L2, right? So of course L is linear because L of alpha 1 v1.
Can we pick f to be? Can we pick f to be the derivative of v and then use Holder's inequality?
No. You can pick v because v is the test function, but what the equation? I explain again. So the equation that you want to show is this equation. So this is a PD, meaning the following. I give you the f, which is a function of x, and which is defined on 0 to 1, right? You have to find the function u, such that minus u second plus u is f, and u also satisfy the boundary condition, which is u0 is u1 is 0. So this f is given, right? This f is given, and your job is to find u, all right? But of course, what I'm saying that for this equation, there is no explicit form of u. One way that people do is to pick up a test function, right? So when you multiply this, you're gonna get this form. So because you solve this equation, this form is true for all of the v. And instead of trying to find the explicit form of u that satisfies this relation, you show that there is one u, such that this relation is satisfied for all of the v, right? So f is given. F cannot be cannot be chosen, right? Now I want to prove this inequality, which is
we defined L of v to be equal to buv. So can we use what we just did with the bilinear form to show that this is bounded by v of the Sobolev norm?
No, because f is given, so you cannot define f. F is given, you cannot change f, right?
No, I'm not trying to. So the integral of fv is equal to buv, right? Because we define buv to be right.
Right.
By definition, or the way that we define the bilinear form.
Right. So they are not equal yet because we are trying to show that there is one u, such that there is this inequality, right? So for now, this b is one separate subject, and this l is one separate subject. And the thing that we have in hand is the Laxman theorem, which says that, okay, if this b satisfies some condition and this l satisfies some condition, then there is one unique u such that you have this equality, right? So what we have done is that you check all of the condition for b that is satisfied. Now we have to check the condition for l. So we know that this is linear, and we want to show that this is bounded. So how can I show that this is right? So how can I show that the interval from 0 to 1 of f v dx is smaller than c times this norm?
Okay, so just apply holders to the integral.
Right.
Then you'll get L2 of f, L2 of v, but L2 of v is less than the less than the Sobolev, right? So then c is just the
Right. So Stephen got it. So Stephen idea is the following. First, you use Holder inequality, right? So you take the absolute value of this guy, and this is smaller than f l squared times v l squared, right? And so this is a constant, but this is smaller than, because we are v is also in h, right? So this is smaller than the v prime L2, right? By the Sobolev embedding theorem. So the L2 norm of v is smaller than the L2 norm of v prime. And so this is nothing but a W012 norm. So you're gonna have FL2 V in W012 norm. So this C has to be the L2 norm of F, right? So I explain again. I want to show that this linear form is bounded, which means that this linear form is smaller than a constant times the W012 norm of V, right? So this strategy will be the same with the previous one. You apply Holder inequality. You have the interval from 0 to 1 of f v dx. It's going to be smaller than f l squared plus v l squared. So this v is smaller than v prime, right? Because of the Sobolev embedding theorem that we just showed. And this is nothing but the L2 norm of the W012 norm. So basically, the C will be f squared. So now we have what? We have L is linear and L is bounded. So all of the condition on L for the Laxman theorem are satisfied, right? So because all of the condition of L and B are satisfied, then according to Laxman gram, there is a unique U such that BUV is equal to LV, and this U belongs to W012, right? Meaning that the integral from 0 to 1 of U prime V prime plus the integral from 0 to 1 of UV will be the integral from 0 to 1 of FV. Right? So this is basically the idea of Laxman gram theorem. So again, so let me explain the intuition of this kind of thing, right? So the idea is the following: given F, we need to find U such that U second minus plus U is equal to F. So this is X, Fx, and this is true for all of the X from 0 to 1. And U at 0 and U at 1, they're both 0, right? So we have to solve this equation in the sense that, okay, you pick any F, so F here is in L2 of 0, 1, right? So you pick any F in L2 of 0, 1, I have to find a function U such that minus U second plus Ux is F, and U at 0 and U at 1 is both 0. So if there is not this term, right? So that if there is no Ux, then things become easy, right? So if we have to solve minus U second is equal to F, then this is easy because you integrate twice, right? And this is easy. Since you can just take this is minus the 2 times integral of F, right? So this is the integral from 0 to T, and then the integral from 0 to X, and then here you have S, the S, and after that you just take another so you just take twice the integral of F, and then you get U. Then this is explicit solution. So the easy case for all these is that you have U second is equal to F. So if I want to find a function F such that I take 2 times the, so if you give me a function F and you ask me to find a function U such that minus U second is F, then I just have to take twice the antiderivative. That is easy. So in this case, you have an explicit solution. But if you ask me to solve something harder, you give me a function F and you want me to find a function U such that U second plus U is equal to F with the constraint that U at 0 and U1 are both 0, and this is satisfied on 0, 1. Then this is a much harder situation. So in the case of star, we don't have an explicit solution. All right. So in the case of this case, you don't have an explicit solution. So what you have, so you have to use the weak form. The weak form is to transform this equation into the following form. You have U prime of X, V prime of X plus the integral from 0 to 1 of Ux, Vx, and this is equal to the integral from 0 to 1 of Fv. And this is true for all of the V, right? So if this is satisfied because this is true pointswisely. So I multiply this by V and I integrate, and this is satisfied. So basically, instead of solving one star, instead of solving the first equation, we solve the second equation, right? So instead of solving this complicated, which is quite hard equation, you solve something which is which look more complicated, but it's easy because you have in hand the Laxman-Graham theorem. And the Laxman-Graham theorem tells you that the second equation has a solution U, and U is unique. All right. So how do you so now by Laxman-Graham, you know that this equation has a unique solution. But how do I find this solution? So to find this solution, you have to use a method which is finite element method. So we're gonna study a little bit about finite element method using Laxman-Graham in the on Friday. Any questions? It's clear. All right. So if there's no questions, we can stop here. See you on Friday. Bye.
Thank you.
Bye.
Thank you.
See you Friday.
Bye.
Thank you. Bye bye.
Bye.